Chapters 21 and 22 both deal with the concept of aromaticity. Aromatic compounds have unusual stability even though they possess many pi electrons. For a molecule to be aromatic, as we will see in the textbook, it must have several criteria met. First, it must be a cyclic molecule. Second, there must be 4n plus 2 pi electrons in the molecule, where n equals an integer. If you can satisfy the equation 4n plus 2 equals the number of pi electrons, then that criteria has been met. The molecule must be flat, with every atom being sp2 or sp. Those are a trigonal planar geometry or a linear geometry. That way, the p orbitals all have the same orientation. And finally, each atom must be able to resonate. Resonance is not possible unless you do have sp2 or sp hybridization. So really, this is just a restatement of Rule 3, but a good thing to keep in mind. Okay, so keeping in mind that every one of these molecules has rings where all the pi electrons are included, I put a check mark on all of those. Rule 2, 4n plus 2 pi electrons, molecule 1 satisfies for n equals 1. N equals 1, 4 times 2 plus 2, 4 times 1 plus 2, equals 6, which is the number of pi electrons. 2, 4, 6. Once again. 2, 4, 6. This molecule, 2, 4, 6, 8, 10, 12, 14. 14 pi electrons solved with n equals 3. This molecule, 2, 4, 6, 8, 10, 12, 14, 16. Can't solve with an integer because n equals 4 gives 18. 4 times 4 plus 2 is 18. 4 times 3 plus 2 gives 14. So 3.5 is not an integer, so we have what's called an anti-aromatic molecule here, if this is the only rule that's not obeyed. So to repeat, an anti-aromatic molecule obeys all the rules except for Rule 2. So if Rule 3 and 4 are satisfied, we're going to label this as anti-aromatic. Molecule D appears to have the same number of pi electrons as A, and so does E. Once again counting 2, 4, 6 pi electrons for each molecule. There are no pi electrons other than this pi bond here and this pi bond here. That's 4. So n would equal 1.5 for this one. Once again, if all the other rules are obeyed, then we are anti-aromatic. Otherwise, just not aromatic. This molecule presents an interesting example. I'd like to remind you, to be an anion, you have to have a lone pair. And before we do part 2, we're going to discuss when lone pairs will be used to create aromaticity and when they will not be used to create aromaticity. For now, let's just accept the fact that we are going to use that lone pair. We're going to put the pair of electrons in a p orbital, which means it can be used to resonate with other p orbitals, such as these two carbons p orbitals and these two carbons p orbitals. So counting pi electrons as those living in p orbitals, we have 2, 4, 6. That fits for n equals 1. With the first 3 molecules being all sp2 hybridized atoms, and the name of the geometry for sp2 is trigonal planar, then rule 3 is obeyed because planar and flat are synonymous. Molecule D is not planar for this reason. The atom I labeled X here is an sp3 hybridized carbon, and sp3 carbons are not flat. They are tetrahedral. Atom X in this molecule is sp3, as is atom X in this molecule. sp3 is tetrahedral, which is not flat, and because of this, resonance in a circle is not possible, and the molecules are not aromatic. This atom up here in this molecule, this carbocation, is sp2, which makes it flat. It has an empty p orbital, which makes it able to resonate with any of these pi electrons. And there's a correct number of pi electrons there, as we determine in rule 2. So this flat molecule should be able to resonate freely, as should the molecule C and B and A, which puts them in the aromatic category. Aromatic, aromatic, and aromatic. Molecule D, because it's not flat, can't resonate in a circle. Because the resonance stops at an sp3 atom, you can't go through there. Same story for molecule F. sp3 carbon prevents resonance around the circle. Rule 3 seems to be violated here because we learned that lone pairs live in hybrid orbitals, which would make the carbon on the top with a sigma bond to H and 2 sigma bonds to carbon, and a lone pair requiring a 4th hybrid orbital to be sp3. There will be a video shortly about how we can rehybridize from the less stable sp3, more stable sp3 lone pair to a less stable p orbital. And the reason we would do that is because when we gain the resonance that's called aromaticity, it more than compensates for the cost of using a p orbital for a lone pair. That deserves its own video. So for now, if you need to use a lone pair to get up to the magic number 4n plus 2 equals 6, in this case, 2 for pi number 1, 4 for pi number 2, and 6 for lone pair in a p orbital, then you need to use the lone pair. After you do that, then you have a p orbital that's fully able to resonate. You've rehybridized to sp2, which is a flat geometry, and you can resonate around the ring, making this one aromatic. Finishing up, this molecule C is anti-aromatic because, as we foreshadowed before, if all the rules except for rule 2 are followed, then you have a molecule that has all the criteria correct except the wrong number of pi electrons, which means it does not want to be aromatic, for reasons I will discuss later. The last two, D and F, had multiple failures of aromaticity, and they are simply Na, not aromatic. And not aromatic. I hope you found this video useful for determining aromaticity of molecules.